Tomorrow between 2:30 and 4:30, you can expect to see a or I will have my study session in 105 in case you're ready to start preparing for your exam on Monday. Okay. So when we last met, I briefly introduced integrated rate laws and briefly introduced method of initial rates. As you've got a little bit of experience because that was one of the key components of the lab is using those concepts, but today we are going to get into working with that in greater detail. So let's see. We are going to evaluate the following information using method of initial rates to determine the order with respect to ICL and hydrogen for this reaction. Now, multiple experiments were run. And we have the initial concentration of our ICL and of our hydrogen. We were also given the rate, the initial rate for this reaction. So we ran 4 different experiments. The first experiment had an ICL concentration of 1.5 and a hydrogen concentration of 1.5 with the rate being 3.7 times 10 to the minus 7, and that is in molar per second. We had a second experiment, which was 3.0 for our ICL, 1.5 for the H2, and it had a rate of 7.4 times 10 to the minus 7 molar per second. Our third one had a concentration of ICL of 3.0, 4.5 for our hydrogen, and that had a rate of 2.2 times 10 to the minus 2.2 times 10 to the minus 6 per molar per second. I'm sorry, there was only 3. Instead of 4. Okay. So in the method of initial rates, you can determine the order with respect to one of the components by holding the other component constant. And the reason this works is we can write, for example, with experiment 1, you could write a rate law for experiment 1, that is the rate for experiment 1 is equal to the rate constant for the reaction times the ICL for experiment 1 raised to its order times the hydrogen concentration for experiment 1 raised to its order. And we can do this for each one of our experiments. So for rate 2, that would be equal to the rate constant times the ICL concentration for experiment 2 raised to the order times the hydrogen concentration for experiment 2 raised to its order. Now, if we were to take and plug in values for what we just wrote, we would have 3.7 times 10 to the minus 7 is equal to the rate constant times 1.5 raised to x times 1.5 raised to y. And we would have, for experiment 2, 7.4 times 10 to the minus 7 is equal to the rate constant times 3.0 raised to x divided by 1.5 raised to y. In other words, the reason that the method of initial rates works is, again, you're taking only one substance that undergoes a change. The other one is being held constant. And by holding that particular one constant, it completely cancels out, as does the rate constant. So that really does simplify the problem, and we can solve for just one variable at a time. So this becomes 3.7 times 10 to the minus 7 over 7.4 times 10 to the minus 7 is equal to 1.5 over 3 raised to the power of x. When you key in the left-hand side, it's 0.5. That is equal to 0.5 raised to the power of x. Now, this one should be fairly obvious, because number one, if anything gets raised to a power of 0, it goes away. It's 1, basically. Anything raised to 0 is a total of 1. Anything raised to 1 is itself. So it should be obvious, but if it's not, you can solve it by taking the natural log of both sides. And when you take the natural log of the right-hand side, the x comes out in front. And then you can divide both sides through by that natural log of 0.5. And so our x would equal 1. So again, I did the longhand version, folks. You don't have to do all of this. I wanted you to see why it works, and it works because when you're holding one of them constant, it gives you the information for the other one, because since you held one constant, that one goes away. So we'll need to do this. So this would give us the value of x, because what we did is we held the H2 constant. To get the order of the ICL. Now to do the other one, we need to hold, in our next one, we need to hold the ICL constant. To get the order of H2. So we would be looking at experiment 2 and 3. And folks, I've been doing 1/2. I could also do it as rate of 3 over rate of 2. In other words, it doesn't matter who's in the numerator and who's in the denominator, as long as you're talking about keeping it consistent across the entire thing. So I can do it on, I've been doing it where I just did the first experiment over the second. It doesn't have to be, it can be the second over the first. It doesn't matter as long as you're keeping consistency. So in this particular case, let's go with, we have 2.2 times 10 to the minus 6 over 7.4 times 10 to the minus 7. Since we're holding ICL constant, that means it comes down to the H2 concentration, which was 4.5 over 1.5 raised to the Y. This first one basically comes out of the 3, and so does the other part, which is 3 raised to the Y, which we can get rid of the power. And when we do so again, it comes out with a Y equals 1. And yes, if you're confident in your math, you can skip some steps here. That's showing all the steps. So when we write our rate law, the rate law for this reaction is that the rate is equal to the rate constant raised to ICL to the 1 and H2 to the 1, because we determined it was first order with respect to each. Now, most of the time, you're not going to see ones. You'll see other numbers, but not the 1. And if that's the case, then it means the same thing. These two mean the same thing. You just aren't necessarily going to see the 1. So literally, folks, this rate law says that it is first order with respect to ICL. It is first order with respect to H2, and it is second order overall. With the overall order here being the result of these superscripts added together. Now, you've read it on multiple occasions, but what does that mean for the speed of the reaction, which is the rate? Well, let's think about this. Let's think about what doubling the ICL concentration did or does. And let's look at it from a rate law perspective. So if you have the rate is equal to K times, say, 1 raised to the 1 times H2, and we were to change that and double the ICL, what's it going to do to the speed of the reaction? It doubles it. So doubling ICL will double the rate. If we double the H2, again, you have your rate is equal to K times your ICL times 1, and rate is equal to K times your ICL times 2. What does it do by itself? To the rate, it doubles it. Now, in other words, folks, there's really no, when you learned back when we did the graphing lab, I said, if you, if it's first order, if you double it, what happens to the rate? There's no secret, it goes back to the math. Now, what if you double the ICL and the H2 concentration? So we went from rate is equal to K times 1 times 1. And now we're at rate is equal to K times 2 times 2. It quadrupled it. There's no secret here. It's just the math.
Would that be equivalent to K to the fourth?
What now?
Would that be equivalent to K to the fourth?
No. Because K to the 4th would mean 2 times 2 times 2 times 2. But it would be 4K. Okay, so let me give you one to do. Find out. And Luna and I will walk around. Let's look at. We're going to look at the reaction S2O8 2 minus plus 3I minus goes to form 2SO4 2 minus plus I3 minus. We have multiple experiments again. The initial rate for, or the initial concentration of the S2O8 2 minus is going to be 0.15. For I minus, it is 0.21. And that has an initial rate of 1.14. Then we have 0.22, 0.21, and 1.70. And then finally, we have 0.22, 0.12, and 0.98. Determine the rate law, well, the order with respect to the F2O8 and the order with respect to I minus, and write the overall rate law.
No grumbles. No grumbles, sorry about that. Oh, you said, let's say hello. Say hello. It's a nice lady. See everybody. Oh, awesome. As long as it's all the way across, if you put one on top, it's all the way up. Ourselves, we're paying. Go. Are we gonna include the 230 minutes already? Oh, yeah. Sorry. I just like to get on concepts for a second, but then I understand why it's not.
You should have found a 1-to-1 ratio. That they were both first order with respect to the two components. So for the first one I did, what I wound up doing is I wound up get S208. I wound up using experiment 1 and 2. And I did 1.70 over 1.14 is equal to 0.22 over 0.15 raised to the x. And when you solve for x, you got a number. It was a little bit over 1, but it rounded to essentially 1. And then for the for I minus, I got I did 1.70 over 0.98, and that was equal to 0.21 over 0.12 raised to the y. And when I solve for y, I got a 1 as well. Any questions? One thing I want you to note, when you talk about the rate law, the overall rate law one thing you should know is that it is not related to the coefficients. In the balanced chemical equation. It's not related to those. Sometimes you get lucky and you could use the coefficients, but most of the time it's not necessarily related. So that's one thing I wanted to draw your eye to. In this particular case, we had 1 S208, 2 minus, and we had 3 I minus in the original reaction. But the rate law has nothing to do with those coefficients. The overall rate law does not have anything to do with those coefficients. So that's one thing I wanted to bring your attention to, because a lot of times when we've done chemistry, we say, look at those coefficients, look at those coefficients. Don't look at the coefficients for rate laws. You can't. Because basically keep in mind, it comes down to how many molecules are colliding at a time. Any questions about a method of initial rates? Yes.
I guess I don't understand why we're doing it. So how is
it applicable? So it's applicable so that you can understand how a particular component in a chemical reaction impacts the speed of a reaction. I mean, if you want something to go creepily slow, then put it to the 0 order, because that means it doesn't have any impact on it. So in other words, it's telling you how fast the reaction is going to go based on that particular component. Other questions?
I have a question.
Yes.
What's the prompt gonna look like? You're gonna give us data, but is it gonna ask?
Using the method of initial rates, determine the rate log for this reaction. Something like that. Okay, So I'll tell you which method to use. And this is the method of initial rates. Now what we're going to do is we're going to move into the integrated rate laws, which I actually find to be the most I find it to be more enjoyable, but most people probably wouldn't agree. But before we get into the integrated rate laws and using them, I actually wanted to come up with the table that I had started, but I've got more pieces to it than I had given you on Wednesday of last week. So if this table is very useful and you may want it on a separate sheet of paper for a study guide, because it kind of sums up the integrated rate loss to a large extent. Now, technically, I'm only going to go for 0, first and second order, but you can have third order, you can have a half order, you can have a three pass order. It doesn't have to be a whole number, and it doesn't have to be 0, 1, and 2. We're sticking to 0, 1, and 2 for the time for our purposes. But keep in mind, it does not have to be that. So I am going to, we're going to deal with the order. We are going to look at the integrated rate law. I am not going to do the calculus to solve the differential equations to get to the integrated rate law, because I expect you to be using them, not having to derive them. We are going to talk about the slope. We will talk about the units of the rate constant. We are going to deal with the half-life expression. And ultimately, the graph, which I'm going to have to come back in and do, but I want you to save a column for that. If I can't move my thing over. Okay. So for a 0 order reaction, if you have a 0 order, by the way, folks, it means the concentration of that component has no impact on the speed of the reaction. That's what a 0 order means, because anything raised to 0 is equal to 1. So if you have a 0 order reaction, it means that substance has no impact on the reaction at all. Now, when you have a 0 order reaction, the integrated rate law is going to be the concentration, the initial concentration. I'm sorry. No. The concentration at a given time is equal to a negative KT plus the concentration, the original concentration. This is an equation for a straight line, and therefore the slope is equal to the negative of the rate constant. The rate constant itself will have the unit of molar per second. And the half-life expression is T1/2 is equal to the original concentration divided by 2 times the rate constant. I'll come back to the graph later. But just don't have enough space. So last week, you didn't have a zero order. But if you had have had a zero order, when you graph y equals mx plus b, the y would have been the concentration at a given time is equal to the slope times the time, which was on the x-axis, plus the initial concentration. In other words, this is a great way also to determine the rate constant because the slope is equal to minus k, folks. Now, one thing we haven't discussed yet is half-life expressions. Basically, what a half-life expression is it determines how long it will take for half of your substance to get used up. That's what a half-life expression is how long does it take for half of the material to get used up. Now, the second one is the first order, which is what you actually determined your dye to be last week, because the natural log of the concentration at a given time was equal to negative KT plus the natural log of the original concentration. This still fits the equation y is equal to mx plus b, where y is your natural log of concentration at a given time. X is the time. But that means that the slope is equal to a negative k. Now the unit force, the slope of a first order is going to be just is going to be per second. So seconds raised to the -1. And the half-life is equal to 0.693 divided by the rate constant. In other words, on first order, the half-life is not dependent upon the concentration. Now, finally, we have second order. And that was the third graph you worked on for each run. And that's 1 over the concentration at a given time is equal to a positive KT plus 1 over the initial concentration. Again, it is still following the y equals mx plus b. Look, where the slope is going to be equal to a positive k value. The unit for our rate constant is going to be per molar per second for a second order reaction, which makes sense, folks. Look at where the molarity is in the integrated rate law. It's in the denominator. So we would expect the molarity to be in the denominator. And then the half-life expression for this is equal to 1 over K A naught. Now, as I did this, when I was talking about the order, the last piece of this puzzle was the graph, and as I kept talking about the order, I said, the integrated rate law, when you take and you actually perform the calculus, it comes out to a straight line. It fits the formula of a straight line. So as we noticed last week, if you graph concentration versus time, you got a straight line. If you did natural log of concentration versus time, you got a straight line if it was first order, which is why you determined that your reaction was first order with respect to the dye, is because when you graph the natural log of concentration versus time, that's when you got your best straight line. And then finally, if you graph 1 over A and that is your best straight line, then it is going to be second order. So with these, what we're telling you with the graph is the graph will tell you which order it is. That's all we're saying. Which one gave you the best straight line? That tells you the order, which is what you did with the dyes. Questions? Okay, so it's about to go ding ding for our little break, and I'm going to get the next set of problems set up while you're doing, because I am going to do some quick graphing. Because we are going to use these integrated rate laws in some determinations. I'll let you take your break. Thank you.
Excuse me.
Yes.
So that 1 over A should be 0, integrated rate law for the is that A original or B?
A not an A original. Same thing.
I'm sorry. Okay, thank you.
No. Stop share here. Yes.
Doctor's appointment Wednesday at 2:40. Is it okay if I just email and find my abdomen in class time?
Well, it's 1 per group.
Oh, just one.
1 per group.
All right. Thanks for that question.
So.
Oh, what are you grumbling at?
People moving around.
Okay, let's get back at this. Let me go share this screen wherever it went. Oh, no, where it goes. Oh. Okay. So I threw up one real quick. This particular reaction, I'm gonna go ahead and let you know that this was a very generic reaction, and I'll show you the reaction in a minute. This reaction was 2 times concentration of A breaks down to 2B plus C. Now, they gave me the time in minutes, and they gave me the concentration of A that they measured at that given time. So this first column was 10 through 60, and it's just done in minutes. The second column was just the concentration that they gave me. Because I know that this is rate law, I automatically did the natural log of concentration. I did 1 over the concentration. I then did a fast graph. Obviously, these are not the way I would turn it in, but it does for the purpose of what I need. I did a quick graph, and in this, I'm looking at my R squared. So if I just graph time versus concentration, I wound up with a R squared of 0.9795, I think is what it says up there. When I graphed time versus the natural log, I got an R squared of 1. And when I graphed time versus 1 over the concentration, I got an R squared of 0.97 something. Because my best R squared happened when I graphed natural log, versus time that says it's first order with respect to A. So now you may say, okay, and I need to write another piece down before I go too far. You may go, okay, so are we going to have to graph? How are we going to graph on a test? The answer is no. I'm going to give you graphs, and you've got to be prepared to interpret. And I will label them and stuff like that. So when I got this, once I decided what my reaction was, I got with the R squared, it was again for the natural log of A versus time. And it gave me an R squared of 1. So I knew that it's first order. And I'll show you what I'm writing in just a moment. And it also gave me the equation y is equal to negative 0.02x minus 4.6. Okay. Now I'm going to stop share this and go back to start share this. Because now we're going to use this information. So I basically, on the screen, all I really did was show you which graph. And these are the pieces of information that I pulled from that graph. My R squared, my best R squared came when I did natural log of concentration versus time in minutes. So that told me it is first order. And that graph gave the equation y is equal to a negative 0.02x minus 4.6. Now, folks, since this is first order, that means that the natural log of concentration at a given time is equal to a negative k times time plus natural log of a naught. So now, what we can do with this information is we can do a multitude of things. So 2a goes to form 2b plus c. By the way, one thing I forgot to mention, and this is actually quite important. Notice rate laws have always been about the reactants only. Rate laws are about the reactants. And I forgot to mention that. That's going to be important later on. We determined that this is going to be first order. Now, if I said, okay, what is the rate constant? What we know is that a negative k is equal to a negative 0.02. So k is going to be equal to 0.02. And because it is first order, the units is going to be per second.
I could say, okay, so what is the concentrate, or, what is the half-life? For this reaction? Because it is first order. That means that T1 half is equal to 0.693 divided by the rate constant. Or in other words, it's 0.693 divided by 0.02 per second. So that comes out to be equal to 34.65. And actually, folks, what have I been doing wrong? Good. Nobody's caught it, and I just caught it myself. Doesn't need to be negative. Comes back up to here. Put something in parentheses for a reason.
Shouldn't it? That should be, yeah.
These are all minutes, not seconds, even though, so in other words, it's really in order of time. So this would be 0. It shouldn't be per second, it should be per minute. Because our time unit was in minutes.
Wouldn't it be minutes to the -1 as well? It's first order.
Or it can be just per minute, that's what the -1 means, so. And this 34 point would not be here. It would be 34.65 minutes. In other words, that per second that I gave you in that, when I was giving you that table was assuming that the time was in seconds, because a lot of times it is. But I actually caught myself because I started thinking back, what was my unit of time? That's why it's so important to pay attention to your units. Even I screw up if I don't pay attention, you know, I gotta improve my units. So what if I say calculate the concentration of A naught? The original concentration. Well, what do we know? We know -0.46 is equal to a positive natural log of A naught. To get rid of natural log, we raise the entire thing to E. So E to the -4.6 is equal to E to the natural log of A naught. That will cause the natural log of A naught, or the E and the natural log on the right hand side to go away. So E to the -4.6 is equal to A naught. Which comes out to be 0.01
0.01 molar, if we want to go that far, is equal to A naught. We can also say, okay, calculate the concentration of A after 70 minutes. Well, going back to our original equation, -0.02x. Y equal to negative 0.02x minus 4.6. You can do it so you can use this equation and go, okay, so our natural log, because you gotta keep in mind what everything means here. Natural log at a given time is equal to a negative KT minus or plus natural log of A naught. So the natural log of AT is equal to a negative 0.02 per minute times 70 minutes. Plus, technically, we could use the value we just calculated of natural log of 0.0101. Or you can do it as natural log of AT is equal to a negative 0.02 per minute times 70 minutes minus 4.6, because we already know that that's the original concentration with the log. No matter which way you do it, you're going to get a natural log of AT is equal to a -6. AT, therefore, when you take the exponential of both sides, is 0.0025 molar. Folks, I could have done other things though. Once I figured out what the order was, we could say, how long will it take for the concentration of A to go from an initial concentration of 0.22 molar to 0.056 molar. In other words, I've changed up what the initial concentration is. But folks, I didn't change the reaction. And the rate law is based off of the reaction. So this is still first order. So it still fits. The natural log of A to the T is equal to a negative KT plus the natural log of A naught. And since it is first order, we can expect that the slope is going to still be negative 0.02 per minute. Because that's the rate constant. It's a constant, folks, based off of the reaction. This equation is based off of the reaction. So in other words, we get our go away. We get our natural log of 0.056 is equal to a negative 0.02 per minute times T plus the natural log of 0.22. So to solve this, we got, let's see, natural log of 0.056. So you get a negative 1.368 is equal to a negative 0.02 per minute times T. So T comes out to be 68 minutes. Technically, almost 68 and a half minutes. There's a lot of information, in other words, embedded in those graphs that you made. That you can pull out about your reaction. And there is a way then to use all that information to calculate new information. Which is what those equations are when we ask you to graph the line. What we're doing is we're giving you an equation that you can now calculate new information from. Got a couple of minutes. So. There is a problem, and I'm not going to actually work. I wanted to see if I can find it. Okay. So there is the reaction of methanol. Ethanol. Breaking down to form an aldehyde plus hydrogen. And I have a set of data here where we're dealing with the time is in seconds. And they're using pressure to determine the concentration because this is all about some gases. So the pressure is going to be directly related to concentration because the greater the concentration, the greater the pressure. Now, when they graphed it, concentration or pressure in this case, versus time gave a straight line. Or the best straight line. With a slope equal to a negative 0.130. So given that information I just gave you, what is the order with respect to the ethanol?
Zero strokes.
It is 0. Because it was pressure versus time or concentration versus time. So we know it was 0. So the rate law would be rate is equal to K times the ethanol. And that's just another way to write it, sorry. It's another way to write the same thing that's on top. Raised to the 0, and what did I say anything raised to the 0 is? 1. Anything raised to the 0 is 1, so that means rate is equal to K. To answer all those questions I gave you earlier, you would be doing, in this case, pressure at a given time is equal to a negative KT plus pressure naught, the original pressure. And you could solve all these pieces of information, given that it would be the exact same way, but now you know what this particular equation yielded. And with that, I will see you Wednesday. 2:30 to 4:30 tomorrow and 1 to 5.